by thanking the organizer for giving me the opportunity to present my work here. And I should also thank them to, because they organize this an ion session, so where we can convince you guys that ions are a great platform where to build a large-scale quantum processor. Okay, so if Norbert didn't succeed with this beautiful talk, well, I will now. Well, okay, maybe that was a bold statement, but yeah, let's say I'll try. You'll tell me later. Okay, so the work I'm going to present today is a recent results where we used a mixed species trap ion quantum processor to measure stabilizers repetitively, okay, and we applied real-time feedback based on the Ancilla readout. So before going into the details, well, let me go to, let me give you like an introduction slide. Feels a bit quite embarrassing, actually, since that we have seen all these many talks in quantum error correction with these very fancy codes like color code, surface code, gauge fixing. Well, the kind of circuit I'm looking at for my experiment is something that looks like this, actually. So it's a very simple stabilizer measurement, right? So let me bring you back to kindergarten in quantum error correction. But yeah, I'm an experimentalist, so I usually work, I have to deal with classical bug correction more than quantum error correction usually, or at the moment. Okay, so those kind of circuits, right? What we need to do is to measure quantum correlation between quantum systems, right, using some Ancilla qubits without destroying information stored in this system. So what this this type of stabilizer measurement does, it's to project the system into one of the two eigenstates of my stabilizer based on the Ancilla readout. And ideally, for quantum error correction, right, we want to repeat this sequence over and over and measure different type of correlations. What kind of correlation? Well, it's up to you. You have to tell me. But this is kind of what we are trying to do. And since I'm an experimentalist and working with a few qubits already hard, I want to recycle my Ancilla, right? So I want to waste as little resources as possible. So this is kind of the theory. Well, in the experiments, instead of having all these many lines for my qubits, well, we had two. So we had two qubits representing the data, the data qubit, and one qubit to be the Ancilla. And the kind of correlation we've been now able to measure are, for example, ZZ or XX. Good. As I said, we use ions as our qubits. So, well, I don't have to explain any more about the basics of ion trapping, since Norbert beautifully explained it before. But, well, for the purpose of this talk, really, what we really need to know is that qubits are, ions are just two-level system coupled to some quantum harmonic oscillators, right? This energy splitting here goes from gigahertz, if we have a microwave qubit, which we have, beryllium, to like hundreds of terahertz, like calcium. It's an optical qubit. And the quantum harmonic oscillator is in the order of like megahertz, up to maybe 15 megahertz for the radius in beryllium. Good. The trap that we use, it's actually this one. It's a 3D trap, so it's composed of a stack of PCBs, okay, with a slot in the middle here, okay, and that's exactly where we trap ions. And these electrodes are also segmented so that we can shuttle ions around, we can split, we can do all this testing for the what is going to be needed for scalability and build a large-scale quantum computer. What is kind of interesting for us is that we can trap two different species of ions, calcium ions and beryllium ions. And in the experiment I'm going to present, as I said, we were going to work with 3 ions, and 2 of them are beryllium, okay, and 1 is calcium. Calcium sits here in the middle. They all the 3 are in the same potential well, so that we can like use the motion as a quantum bus to transfer information around. The 2 beryllium will serve as the data qubit, and the calcium ion as the Ancilla qubit. So let me try to motivate why we need mixed species. Okay, so as I said before, when we want to detect the ancilla and act, well, do some feedback after we do our detection. So we do not have like this tightly focused laser beam to do single line addressing also for the detection. So whenever we apply, if all the qubits were of the same type, whenever we apply the detection laser, we will scatter photons from every single qubit. So we will destroy the information contained in those ions. And that's something you don't want, so how do we solve it? Well, use a different use a different species for your qubit. And this has some advantages. One advantage is that, of course, now whenever you apply your detection beam, only the ancilla qubit will scatter photon. That's because the laser system that we use is completely different from, the laser system that we use for calcium is completely different from the one we use for beryllium. And it also has another advantage, and the advantage is that whenever we scatter some photon, okay, we are going to have some recoil effect. So we heat up the ion chain, and usually we want to be in the ground state of motion to have like nice, good fidelities for our gates. So we can, again, just use the laser system for the ancilla qubit to cool the ancilla qubit, and therefore sympathetically cool also the two beryllium ions that sits together. Remember that those ions are like coupled harmonic oscillators, so that's why this works. Good. So now, why did we choose calcium as the ancilla and beryllium as the data qubit? Well, as I said before, we want to repeat this measurement over and over, right? And we actually did it like up to 50 times. So you need a long coherence time for your information qubit. So for us, at the time it takes to repeat a stabilizer measurement, it's about 1 millisecond. It's not this part, which is like the most consuming part, but it's actually the reset part, because we are doing detection, which takes, 60 microseconds, but then we have like this recooling process I was talking about, which takes on the order like several hundreds of microseconds. So that's why we are kind of forced to use beryllium in our case, because beryllium has a very nice clock transition. So, and the coherence time for this clock qubit is like 4 seconds. So what does it mean, clock transition? It means that we have these two levels, okay, which are first order magnetic field insensitive, in a sense. So if the magnetic field fluctuates, well, what we will see is that the two energy level will move simultaneously by the same amount. So they will maintain the energy splitting. That's kind of the idea. At this kind of high magnetic field that we have to use to achieve this clock qubit, well, calcium has a coherence time of like 1.5 to 2 milliseconds. So you see that if we want to repeat this many, many times, we are kind of forced to use beryllium. And the other ingredient we need for quantum error correction, well, it's feedback, right? Feedback upon detection of the ancilla qubit. And for us, we can do that. It's, well, the branching time, it's at the moment like 50 microseconds is nothing what, well, it's very long compared to what Austin told us yesterday, but, you know, I mean, we can push it down to like 2 microseconds per board, and that's what we are going to try in the future, but it's not really important, because whenever we are branching, we are still anyway cooling. I mean, that's really like the bottleneck of this sequence here. And, well, so basically that's exactly what we've been doing in the lab, and then let me try to go into the details of how we implemented this stabilizer measurement. So I have to say I was kind of envious of your talks before and your slides where you have all these very nice color codes. Well, you have all these nice color plaquettes. Well, and Jonathan was also very usually complaining about the visual appealing of my slides. So I have now also a color circuit. Okay, so this is this bunch of operation that you see here is the core operation that we need to do the stabilizer measurement. So it's not really important to understand what every single pulse does, but you just need to realize that it's a bunch of single qubit gates, and free ion entangling gates. So those are motion-assisted entangling gate in the same way that Norbert explained before. Okay. The nice thing is that it's an entangling gate between mixed species of ions. So we are coupling like between microwave qubits and optical qubits as well. Okay. Well, if we put all these pulses together, what we get is actually a phase shift on calcium conditional on the ZZ parity of the beryllium ions. Okay? So how do we read out this phase shift? Well, we can just embed this core operation into a Ramsey sequence. And effectively what we get is a bit flip on calcium based on the parity of the two beryllium. So this effectively measure the ZZ stabilizer. Okay? So whenever we detect the calcium ion, we basically project the two beryllium ions in one of the two parity states, either the even or odd subspace. Good. So how do we prove that this is a quantum non-demolition parity measurement? Well, the idea is that we need to prepare some known parity states, and we need to check how they look after we apply this operation. So how do we create this how do we create these parity states? Well, we do something very similar to what I said we said before. It's again an entangling gate. It's exactly the same gate as before, except that we do not switch on the laser for calcium, basically. We basically stop at this point here in the gate, and at this point we are kind of in a 0, 0 plus 1, 1 on the two beryllium with some phase. And to rotate the parity, we apply a global pi/2 rotation with some phase. Okay, and by scanning this phase, we can go from odd parities to even parity and so on. Okay, so that's how we input. So that's how we prepare our parity states. So now we can just take those parities and feed them into our protocol and see what happens afterwards. And this is actually what we get. So we get these two curves, this blue and red curve. The blue curve is beryllium in even parity and calcium in a 0 state. And the red curve is calcium in the 1 state, so the other one, and beryllium in the opposite parity. So which is doing exactly, something which is more or less doing what we are expecting it to do. Okay, you see these free poles down here. We have infidelities. It's also not going up to 1. Well, it was nice that we put the label up here, so it's kind of, it's not, well, it's kind of faking it a bit, masquerading it a bit. But anyway, well, we think we understand where the fidelity issue, where the problems are in fidelity. And well, I'm happy to talk about it later. We basically blame everything on beryllium. It's a very nice qubit, but it's a very nasty laser system. Good. So this is not really something new, as it was written also before in the slides. I mean, the Innsbruck team measured those kind of things before, maybe not with a mixed species, but it was something that has been done already like 10 years ago. So people also came up with some measures of fidelities, and especially Markus Müller. So they came up with some measure of fidelities to somehow benchmark our operation. In particular, I can try to give you like a flavor of what do they mean. So we have some quantum non-demolition fidelity. Well, as the word says, it just tells us how quantum non-demolition our operation is. It basically just correlates the input parity states with the output parity states. Okay. We have some measurement fidelity, which basically correlates the input parities with the ancilla qubit readout, right? Because depending, as we said, depending on the parity that we fit in, we want to have one particular state of calcium. And then, lastly, we have this quantum state preparation fidelity, which somehow tells us the correspondence between the measurement of the ancilla and the final parity of the beryllium ions. Okay. So those are kind of the values. It's okay. Good. So before going on and like repeating this sequence over and over, let me focus on a very important experimental detail. Okay, and so let's go back to the core operation I was talking about before, and in particular, actually, let me even consider a smaller subset of it. Okay, as you can see, this small bit here does a phase shift on calcium based on the parity, an XX parity of the beryllium ions. So ideally, we could even like measure the XX stabilizer by just putting a Ramsey sequence around here on calcium and having only this orange block. Okay, there is a good reason why we don't do that, and this is the one. This is it. So the way we run gates in beryllium, okay, is very similar to ytterbium. So we also have a Raman. We also have Raman transistors. So we have these two Raman lasers, whose energy difference is exactly our qubit transition. There are two possible ways we can run these gates, and one is a motion-insensitive configuration, so meaning that the two beams are kind of co-propagating one on top of each other, okay? And in this case, we are not affecting the motion at all, so this is not good for the entangling gate, since I said it's motion-assisted gates. But those guys have a very nice advantage, is that if you look at layout in the optical layout, they follow a very similar path. So the relative phase stability is very long, is very good. So so we would tend to prefer this kind of configuration compared to this other configuration, which is motion-sensitive configuration. The problem is that these two beams follow two completely different paths. One is here, the other one is on the other side of the optical table for us. So it's really like having an interferometer. Whenever you have like any small fluctuation, thermal, whatever, changes the relative phase stability. Okay, and we measure something on the order of 10 milliseconds. So it's something which can be deleterious because it's going to destroy your your operations if you are doing like gates for too long. And unfortunately, this is the one, as I said, this is the one we need to use for our Moment-Sorensen gates. So how do we fix that? There is actually a fix. So let's say first what is the effect. So this means that from shot to shot, the relative phase changes. So instead of having this nice XX type of operator, we have a phi-phi operation, where phi is some angle along the equator of the Bloch sphere, okay? Which is not good, because then if you look at the matrix, is like full of these laser phases that appears. So something we would like to avoid. And how we do that? Well, we can just put two extra pulses, okay? Again, using the same type of configuration, so the same perpendicular configuration, okay? Which are like phase referenced with the Moment-Sorensen gates here, okay? So what happens is that if we do that properly, we end up having a nice diagonal matrix, okay, which doesn't have anymore any phase dependence, laser phase dependence. And so this is exactly the kind of operator we were talking before. So what's the strategy here? Well, the strategy is also now that I can even potentially reset the phase of the laser here and calibrate this as a small block, and then just use it whenever I want, right? And if I want to do any rotation of this operator, I can just use my phase sensitive, my motion insensitive beam configuration to do the rotation. So maybe it sounds a bit vague. Let me try to give you like an example. So suppose that we want to change the base of the ZZ stabilizer. We want to measure, for example, the XX. What I will do is to use again, this this motion insensitive configuration just to rotate the base of this nicely calibrated block, okay? And effectively what it does, it's like applying a Hadamard transformation in front. So effectively what it does is actually putting a phase shift, this should have been an X. It's actually doing, because we have these 2 pi by 2 pulses, it's a bit flip on calcium based on the parity, the XX parity of the 2 beryllium gates, ions. And I can feed again my parity, my prepared parity states, and I can see what happens after. So it's a bit trickier to understand exactly this plot, but it kind of behaves as we expect. So, and with this kind of trick, I can just measure any type of rotation. So I'm not, I don't need to measure necessarily XX, I can do whatever. Good. So with this, we can try to put all these blocks in a row and measure like repetitively these stabilizers. So I can even, as I was saying before, we can even do feedback. So we can potentially stabilize a subspace. Okay, we have 2 qubits. We cannot stabilize a particular state. We can stabilize at least a subspace. So suppose now we want to stabilize the odd subspace. So what happens is that I fit in whatever input state. I do this QND measurement at the end. And depending on the calcium readout, I end up either in the even state or odd state for the beryllium. So if I want to stabilize the odd state, whenever I detect calcium in 0, I apply a correction pulse that rotates the parity. And then I just add these pulses continuously. And we did it actually, and what we obtained is actually this yellow, this orange curve here. Yeah, I mean, we did it actually up to 50 shots. Well, there is no reason why we couldn't go on for longer, but you know, I mean, it was 2 in the morning. I wanted to go home, and the experiment was getting long. Yeah. So what you see here is actually then the probability then of being in the odd subspace here, and we can actually do the same thing where we prepare some some odd parity state, and then do not apply a correction, but just measure the ZZ stabilizer continuously. And what we see is this blue curve here. We did actually up to 20 shots. Okay, so what we see is actually a factor of 3 improvement with and without with a correction. Good. And yeah. So what is kind of the limitation here is actually some intrinsic problem that we're using this Raman transition. So what happens is that I was saying before that we can think of our qubit as a 2-level system, but it's actually not just a 2-level system, right? It's a ground state qubit. It has it's an hyperfine ground state. It has many different transitions. So what happens is that sometimes we just scatter photons out of this. We go out of this Raman cycle, so we end up into some other state. So that's our kind of intrinsic limitation. So this is a 0.2% of resonant Raman scattering per cycle, not per MS gate. So this is kind of our intrinsic limitation, but we can potentially reduce that by increasing the detuning of our Raman transitions. Good. So yeah, it was 2 in the AM, 2 in the morning, as I said, but I also wanted to take other data. So we also tried to do some Bellstate preparation, because now with this tool, yeah, before I was saying that we can measure repetitively the same type of stabilizer, but I also said that we can also measure in different bases. So what I can do if I measure along the Z direction first and then measure on the X direction, well, I'm actually doing a Bellstate measurement, right? So I can prepare a particular Bell state. So suppose now I want to prepare one of the two even Bell state. Okay. So so what happens is that I can input whatever anything here for the beryllium ions. I then correct in the case I have a NOD state. So I will end up with something in the even subspace. I then apply a parity measurement along the x direction, and depending on the calcium output, I will either have the state phi plus or the phi minus. Now, I can also check the coherence of those states, and does it work? Okay, yeah. Those are like parity flops to check how coherent those states are, and I obtain these two curves for the phi plus and for the phi minus. So this is the color. There is this phase shift, which is kind of expected from theory. The kind of contrast is, okay, you see it's pretty small. I mean, it's 76%. This is kind of the contrast. Yeah, we are not happy. We are still trying to, we are pushing up fidelities. As I said before, we are blaming it on beryllium. We already now improved the system quite a lot, and I'm in the process of retaking this data as I go back. So this already brings me to kind of the conclusion. I think I demonstrated the capabilities of our control system. We can work with mixed species. We can read out stabilizers sequentially, and we can apply feedback conditional on the detection. What we need to do still is to improve fidelities. Okay, this is some work in progress. It would be nice also to repeat this ZZ measurement in XX, like to stabilize a particular Bellstate, and keep correcting. And the other thing that we are going to try to do, because Jonathan said that it will make the paper much easier to write. Okay, so I'm going to try that. Is that we want to have some sort of single ion addressing. So I agree with that. It will be much nicer. The problem is that we, differently from the Maryland group, we do not have this nice single ion addressing beam. So we are going to kind of cheat a bit and have like some transport-assisted single ion addressing, meaning that we just translate our ion crystal from the center of the beam. And effectively what happens is that we have two different intensities for the two beryllium ions. So we do a 2-pi rotation on one and a pi rotation on the other one. So effectively we are doing an IX operation. So then we can say whenever we do a ZZ stabilizer, when we do the correction, we can just apply an IX, which is nicely it's easy to, everybody sees that it anti-commutes with the stabilizer, whereas the type of figure we are doing at the moment is like a global rotation, which is a bit more complicated to see. And we can also do like IZ type of operations. Yeah, with that, I want to thank the group, and in particular Jonathan and Vlad, who spent quite some night with me taking this data. Thank you. Was it quick?
Questions for Matteo?